thank you everyone for being here. It's exciting for me to be able to share some of my research and talk to people that don't do the same thing that I do, and get some of your thoughts on the things that we think about pretty much all day long, every day, and share with you today. So let's start. Genome. What's a genome? Who's heard of one? A few of you? What have you heard about it after you finished chewing? No pressure, yeah. Don't choke.
Thank you. I think my definition of a genome is the genetic makeup of something, an organism, or like S1A.
Great. Did everybody hear that? The genetic makeup of an organism. Is that what you said? Anybody else have any additions, comments? Yeah?
The order of the nucleobases in the DNA.
I saw another hand up somewhere else. That's all exactly right. In fact, you hit on the head what a genome is, which is the organization of all the genetic information. And you hit on the head what sequencing is, which is ordering those DNA base pairs. So we can race ahead because you guys are all so advanced. But let me just, for those of you who are not on the same page, use the book, excuse the pun, to get us on the same page. So when we talk about the genome, we're talking about everything, all the genes, all the hereditary information in an organism. And that could be anything from a bacteria to a person. And when we talk about genes, we're talking about specific portions of a DNA code. So the analogy that's helpful is a book where you would talk about the genome being your whole book of you. If I can find a cursor here, no. So the genome would be your whole book. The chapters would refer to your chromosomes, of which we have. And then we have the sentences, which would be considered the genes. So that's how we can talk about the scale of the information in the genome. And sequencing, as someone else has already talked about, is essentially determining the order of our DNA bases, our trinucleotide bases. So these are really large machines that have become cheaper over time, in fact, to actually process and identify the ACG, the order of the A, C, T, and Gs in everybody's sequence, in everybody's genome. And essentially, the readouts, the reports look like this. And then eventually, what we like to do as scientists is compare someone's sequence to a reference sequence, something that we can make sense of, changes and comparisons and duplications and rearrangements. And this is called a circus plot, which is essentially a visual representation of all the chromosomes laid out in a circle. And all the lines in between are essentially all the changes, rearrangements, duplications that happen within all the chromosomes. So there's a lot of actual enthusiasm around whole genome sequencing because it's heralded as bringing us in medicine one step closer to this idea of personalized medicine. Has anybody heard of personalized or precision medicine? What does it mean to you?
You always catch me on a meeting.
Yes.
It's like, because not all, like whenever you get sick, not all diseases are the same. There are different versions of each disease, and depending on that, it should be treated differently. So personalized medicine is made for that specific person, or made for that specific type of disease, or version of that disease.
Yeah. Has anybody heard of big data? Yeah. So genomic data is an example of big data. And personalized or precision medicine are these types of initiatives where we're trying to essentially harness big data, whether that comes from the genome, it comes from lifestyle behaviors, proteomics, any types of big data that we can to then essentially, instead of using a blunt approach to treat a patient or try to figure out the diagnosis or what is the inherent problem with a patient, we try to leverage more data. And genomic sequencing provides more data. And there's been a lot of hype and hope around genome sequencing as bringing us one step closer to personalized medicine. And this has been in all facets of medicine, not just cancer, but these are two examples of cancer where sequencing has helped us with cancer care, because that's the focus of my research. So these are examples where genome sequencing has been helped to identify the causative mutation of a person's cancer, or in the Vancouver Sun article shows an example or describes an example where sequencing was used to basically identify therapy for a cancer patient's tumor that was unresponsive to standard care. So what we typically do with cancer patients, and that's become standard in the US and somewhat becoming standard here in Canada too, is that lots of cancer centers or cancer hospitals will take the tumor sequence, take the tumor DNA from a tumor and actually sequence it to identify the order of the DNA sequence, but then identify changes that are specific to the tumor that don't necessarily exist in the rest of the body, and then identify potential treatments that could actually be specific to that person's tumor and potentially allow that tumor to respond and therefore shrink in that person. So there's many examples where potentially a breast or a bladder tumor has been resected, been removed, and we sequence that tumor's DNA, get the sequence, and we see that actually there's a lot of mutations that are similar to colon cancer mutations in that person's tumor. Why don't we take drugs that have been used in colon cancer patients and try to use that in this breast cancer patients to essentially see if this patient will respond to this therapy. So those are examples of tailoring treatment or personalizing treatment in the cancer care context where we've been using sequencing in that domain. And there has been, largely precipitated by the significant drop in cost of sequencing, a real huge concomitant increase in the number of human genomes that have been sequenced around the world. So what used to be $3 billion to sequence one person's genome in the late 90s has dropped to just over 1,000 US just after 2010, and has essentially created a lot of excitement about how we're essentially going to be able to now scale up genome sequencing and provide this more potentially more at a cost-effective level in clinical care, in our healthcare system. But of course, the costs downstream to actually analyze the data and make sense of it cost way more than $1,000. So we have to just keep that in mind. And there have been national efforts around the world to actually scale up genome sequencing and apply and offer sequencing to swaths of countries. So you might have heard of the Personalized Medicine Initiative in the US. That was a signature initiative of Barack Obama's, where they're essentially trying to create a research study, national research study, and sequence 1 million US citizens' genomes to essentially harness that data along with other forms of healthcare and lifestyle behavioral data to essentially try to bring the understanding, etiology of basic diseases and potential treatments of cancers and other rare conditions to bear. We also know of the UK 100,000 Genomes Project, which is actually taking the same concepts of sequencing 100,000 genomes of various patient communities. But what they've done, which is actually quite interesting, the National Health Service there is actually trying to actually integrate that sequence data right into the healthcare system and use it in real time, which is actually a fascinating national human experiment of how we can actually adopt and implement genome sequencing at a national level right into the healthcare system. There's a bit of a disclaimer, because right now we don't have the amount of evidence to support whether it's clinically effective to do so, whether it's cost effective, whether we have the healthcare systems in place to actually be able to sequence patients rapidly, interpret their data, give them the results, figure out what to do with their data, and then deal with all of the health service delivery and potential ethical issues that come. And that is a mapping of what policymakers need to consider when they choose to fund a new test, a new device, a new drug in our healthcare system. As you know, our healthcare dollars are determined by provinces, and we have in every province policymakers that sit down and review the evidence of any new technology, any new test, any new device, any new robot procedure that they want to fund or that a hospital is asked to fund in the province for all of its citizens. And they have to go through the data and say, is it safe? Does it do what it's supposed to? Is it effective? Is there any utility in the information? Is there a clinical intervention, a treatment, a screening approach? Is there anything that we can do with the results after? And really, is the data itself accurate that we get? So all of these issues around clinical utility, clinical validity, the analytic validity are all, and the facilities in place, the health service impacts, and the costs are all what policymakers need to take into account. And this kind of evaluation is generally called health technology assessment. And what's interesting is while there are health technology assessment agencies all around the world and in every country, in almost all provinces in Canada, Ontario and several other jurisdictions around the world are one of the few that have a health technology assessment, essentially policy unit, essentially dedicated to assessing genomic technologies and making funding decisions based on the evaluation of that evidence. And that just goes to show the increasing importance that genetic and genomic technologies are going to have and the importance they bear on increasingly being adopted into our healthcare system. But as I've already suggested, we have significant issues when it comes to sequencing, genome sequencing, specifically in terms of analytic validity, in terms of does the test what we're thinking it's testing for? Is it actually doing what we're picking up and sensitive enough and specific enough and accurate enough of a test? Well, we have computation and technical challenges because, in fact, the sequencing, which is the ordering or determining of the actual ordering of our base pairs, is kind of varies in coverage, which means cover in the depth or the amount of times or the accuracy of the reads, so of the sequencing, of the sequences. So we have a challenge, depending on the technology that you use, that we're not going to have great coverage for the areas of the genome that might be missed in a person's test. We also have bioinformatics challenge because if you can imagine, a sequence covers terabytes of data. Someone needs to sift through all that data and make sense of it and interpret what the clinical, what does this data mean? What am I supposed to tell a patient? And what can we do about this data? What can we do with this result and help this patient? And that is called bioinformatics. And that requires a lot of software, a lot of algorithms, a lot of programming. And so we've got a human sort of bottleneck as well as technical bottlenecks just with analytically analyzing the data that comes out from genome sequencing. We also have a challenge right now, just because of the state of the science, is that we don't understand the whole genome yet. We don't know what the clinical implications are for every single genetic change or variant that we discover in someone's genome. That's just because not every single part of the genome we understand to be associated with a disease. We're still learning about the association of specific mutations or genetic changes or variants with disease. So a lot of the time, and a lot of the information that's generated is what we call variants, genetic changes, of uncertain significance. We don't know what the data means. And we are often saddled with a lot of variants of unknown significance that get generated from genome sequencing. And so that creates a challenge for a policymaker that says, I've only have a small little budget that I need to allocate to a new robot in a hospital or potentially this new fancy test, but what can we do with the results of this test and how does this help patients? The other thing is that the clinical utility, how useful is the test? Well, again, I just told you that much of the information we don't necessarily understand, but a few of those variants or genetic changes that get read out, that get sequenced, are going to be what we call medically actionable, which means that that's a mutation for which there's a clinical intervention. So who here has heard of BRCA1 or 2? The sort of Angelina Jolie classic story? Not really, no? So the BRCA1 or 2 gene is pretty much famous, or rather Angelina Jolie has made it famous because she chose to publicize her story of choosing to undergo a genetic test for this particular gene because her mother and her grandmother were actually died of ovarian cancer. And so she thought that, maybe I have a hereditary predisposition, and that BRCA1 and 2 mutation is one of the few genes that are associated with a hereditary form of breast and ovarian cancer. Yep.
How can we detect the genetic mutation using the sequence we got from the genome?
You look at every single variant, and you look at the genes, and then you correspond it to the genes. So there's basically databases that you then align and do that type of analysis. That whole bioinformatics piece that I was just talking about is exactly that process. You look at the readouts, then you go to databases that exist to say, this section and these genes or these sections of the readouts have been associated with diseases. This is the literature or evidence base that shows you all of the studies that have proven that there's an established link between that gene mutation, that variant, and that disease. And then the next thing is there anything we can do about giving someone a drug or giving them a test or surgery to try to reduce the risk of having that disease in the future? And that's pretty much what medically actionable variants mean, that they have any medical intervention that someone could take to act on that variant. And unfortunately, very few of what we generate from genome sequencing are considered these medically actionable variants. The other thing, of course, is if we start to generate a whole bunch of information that we don't necessarily know what it means, or that might not have any clinical interventions available, then is there a chance that patients that are equipped with this data are going to potentially use various tests, ask for various services in our clinics by doctors that might necessarily not have been appropriate for their care based on the test results? And will that lead to increasing inappropriate, unnecessary costs in our healthcare system? So these are the type of the policy challenges that people in these health technology assessment agencies in our provinces, in our states, in our territories, and in countries think about when they think about funding a new test and technology. And then, of course, they think about, okay, if we make this available and we roll this out, do we have the clinicians, do we have the staff, do we have the machines and this capacity for anybody to actually order the test, understand the test results, and then know what to do and help their patients with it? We have to make sure that we have the resources and the skilled force to deal with this test. And then finally are the ethical issues. Clearly in genetics, and now in genomics, we have a lot of things to think about. You can imagine just the issue of a consent. Having a patient think about and make an informed decision based on all the risks and benefits, all the limitations, and the challenges that I've just described to make sure that they understand that. That's a huge task. And imagine when a patient's already saddled with just dealing with their illness and is being offered this test as another option to find a diagnosis for their disease or a diagnosis in their family. This is a lot to consider. The other issue, ethical issue that comes up when we talk about any technology, but especially when we talk about expensive genomic technologies, is equity. Having appropriate access and potentially equal access, if appropriate, for everyone, not just those who can afford it or jurisdictions that can afford it. And then the duty or obligation to recontact. I've just told you that the state of the science is changing. Our understanding of what a genetic variant or a genetic change means today will change over time. So what we previously might have called or interpreted as a variant of unknown significance, a VUS, might change over time to become something that either is important for a person's health or benign, unimportant. And what is the obligation for a clinician who orders these tests or a lab that runs these tests to recontact patients and their family over time as our interpretations and knowledge of the science changes? And finally, my favorite topic of ethical issue du jour is incidental findings. Genome sequencing is almost a blunt approach. It's bringing out the big guns of sequencing a person's entire genetic code to find the needle in a haystack, to find that diagnosis, to find the genetic mutation or change in a person's tumor, for example, that will help us specify new or identify new treatment, for example. But along with finding that needle in the haystack, we're also going to be finding a whole bunch of other needles that we weren't looking for, that were incidental or extra or unexpected for the patient and the doctor. And so this actually is a very important issue, because in the process of decoding a person's genome or the genome of their tumor, we're going to increasingly be uncovering incidental information. And this information, what does this information look like? Well, it's anything that we know of and understand in your genome. So these can be genetic changes that are associated with how you respond to a drug. Do you metabolize it quickly or slowly? Or are you at risk for having an adverse drug reaction to that drug? We can learn that extra information. We can also learn whether you have a several-fold increase in a common disease like heart disease, diabetes, or other common cardiovascular risks out there. We can also learn that actually we've just uncovered a mild condition of a disease that you didn't actually know that you have right now. So we could be unknowingly diagnosing someone with a current disease. We can also be finding risks for potentially distressing neurological conditions like Alzheimer's or Parkinson's. And then, as I've already told you, we're going to be uncovering a whole swath of variants of unknown clinical significance. But that's the scope. The scale is also quite significant, because for every person that is sequenced, the data shows that while only a few, up to 6%, will find these medically actionable sort of home run variants where we have clinical interventions, a treatment, some screening, or a surgery that we can offer to reduce a person's risk. But up to 89% of participants that get their genome sequence could find out that they have risks for these drug reaction variants, or variants that will basically tell them that despite the fact that they don't have a condition, they're still at risk for passing this on to their children or their grandchildren, which we call carrier status. So let me just bring this point home with an illustration. So this is a circus plot of a female patient back in New York at Memorial Sloan Kettering Cancer Center. All of her chromosomes are arranged here, 1 to 22, and XY. She's a girl, so she doesn't have anything under the Y chromosome. And it shows all the rearrangements and duplications and all these kind of things in here, right? And all of the coverage issues are going all around here. So the story is that she was suffering with breast and ovarian cancer. She has a long family history of breast and ovarian cancer. Let's offer her BRCA1 and 2 testing. But she tested negative, but it was still such a strong family history that there must be something genetic happening for her. So we offered her genome sequencing. And in fact, they did find a PALB2 mutation that explains what's going on in her family, which is wonderful news, because not only can we identify and tailor and manage her cancer, but we can now offer her whole family sequencing for this mutation too, to identify anybody else that's at risk. But what we also uncovered are all these incidental findings that we weren't looking for. Her increased risk of aortic aneurysms, thrombophilia, polycystic kidney disease, and actually the list went on, but I couldn't fit it on the slide. So we were saddled with the question of what do we do with this information? She didn't ask for this. We didn't consent her for this when we offered her this test, but yet we're holding essentially a hot potato in our hands. What do we do with the information? So guidelines around the world have actually started to coalesce around a consensus that there's an emerging obligation to disclose incidental findings that have been identified in the course of sequencing. Whether you sequence for a patient in a clinical, in a hospital setting, or you're doing it in research, if you find at least the minimum being medically actionable variants, then you need to disclose those to your patients. And in fact, you need to consider what they want to know in advance to even having the test. When you ask patients in the public what they want to know incidental findings. The vast majority, 97%, want to know medically actionable results, incidental findings, variants for which there are clinical interventions to reduce the morbidity and mortality associated with that condition. They also, 80% want to also know medically actionable results that we don't really have anything to offer you to necessarily that are proven to reduce or prevent the condition. Possibly a bit more concerning is the fact that 74% also want variants of unknown significance. Scientists don't know what they mean, doctors don't know what they mean. I don't know what we're going to tell the patients, but they want that back too. But the point is that most everybody wants all results and very few want none. But put yourself in a position of having your whole genome in front of you and choosing anything under that sun to learn. How would you make that choice? Do you want to know your risk for colon cancer, for brain cancer, and Alzheimer's disease, and study on cardiac death, and how you metabolize certain drugs, and your risk for passing on conditions to your children or grandchildren, and your ancestry, and the list just goes on. And simultaneously, you need to consider all the risks and benefits of all of those conditions with all of the different variants and associated increased risks for all those diseases all at the same time. Can you imagine how you'd feel? Potentially drowning under a fire hose. And imagine you're a patient who's suffering from a condition. You need an answer for what is going on. The doctor's looking for ways to help manage your care, treat your disease. And then this tsunami of other incidental information that is placed on your plate. That could be a lot to take in, especially since a lot of this is hereditary and it's not only affecting you, but your family. So what we've done in my lab is create a decision aid to help patients make sense of, learn about, and make informed choices about what they want to learn from their genome if they're having their genome sequenced and being offered incidental information. We start off with a video that explains all of the things I just told you. Then it goes through risks and benefits of learning about different kinds of information from your genome. Then we do a little small true and false knowledge quiz to make sure that people really understand what we're talking about, and then give them the opportunity to work back to various parts of the video to make sure that they get it. And then we ask them to make a choice. So what I'm going to do is just give you a little snippet of the video just so you get a sense of what a patient would see.
Hi, I'm Dr. Mike Evans. There's a new kind of powerful test in town, and it's called genomic sequencing, where we don't just map one gene, but your whole genetic code. Genomic sequencing is evolving quickly. Its use is still uncommon in the clinic, but this is starting to change. The thing about genomic sequencing is that it can provide us with useful information, like helping your doctor identify a genetic cause for your condition or help her tailor your treatment. But the thing about genomic sequencing is that it can reveal a lot of extra information about many other disease risks which are unrelated to your condition. This is what the geneticists call incidental or secondary findings. Some of this extra health information might be helpful, some might be confusing, some might cause anxiety, and much of it we simply don't know what it means for your health yet. The good news is that you have a choice as to which incidental findings you want to learn about, and can think about this in advance. And in this whiteboard I'm going to give you the basics and a bit of a framework to reflect on. Okay, now that I've got your attention, let's do a little genetics 101. Your genetic information is contained in your genes, which hold the instructions for your cells in the form of DNA. You've probably heard of the long, twisty ladder or double helix, which is the structure of DNA. You can think of your entire genetic makeup as a book. For a while we've been able to read pages of this book, or a few genes at a time, but now we can read almost the whole book. It's what we call a genome. Reading most of, or your whole genome, is called genomic sequencing. As we mentioned at the top, when we map your genome, we get what my kids would call TMI, too much information. So to help you decide in advance what you want to know about, it may be helpful to think about your genome as a book, divided into 5 chapters or categories of disease risks. This will help you decide which categories or chapters of your book you want to open. Category 1 is what we might call the most actionable. Here we can discover whether you have a gene that has been clearly shown to raise your risk for certain diseases, and where there are proven therapies or preventative strategies available to help reduce your chance of developing those diseases. Category 1 can also tell you about your response to certain medications. For example, in the course of a medical workup to find a genetic cause of a woman's condition, a doctor orders genomic sequencing and happens to also discover she has the BRCA1 or 2 mutation, kind of like a spelling mistake in that gene, which puts her at high risk of developing breast or ovarian cancer. This BRCA1 or 2 mutation is an example of an actionable incidental finding because we have a preventive strategy, such as increased monitoring, mammograms, or MRIs, or some women may choose to have surgery to remove their breast and or ovaries. These are all proven strategies to help reduce chance of developing breast or ovarian cancer. Category 2 includes your risk for common diseases such as type 2 diabetes, heart disease, and some cancers. This may sound helpful, but it's really important to know that these changes in risk are typically small. And that's because these common diseases are caused by multiple genes, some of which we know of and some of which we don't. Either way, your genes reveal only part of your risk. Other factors such as diet and exercise, life circumstances, they may all play a much stronger role. So you can change your lifestyle, better diet, exercise more, smoke less for sure, but beyond that, there aren't proven medical interventions to reduce these disease risks. Small changes in risk can be hard to put in perspective. Let's say genomic sequencing shows your risk of type 2 diabetes goes from 10 to 13%. How do you frame that? Do you say to yourself there's an 87% chance I won't get diabetes, or a 13% chance I will? How do you take into account the fact that only about a quarter of the risk for type 2 diabetes is genetic and 3/4 is brought by your lifestyle behaviors? Will this data help you be more vigilant about exercise or diet, or too vigilant about common symptoms that you think may be a sign of diabetes? Now, category 3 can reveal current or future genetic diseases. So, for example, muscular dystrophy, a genetic cause of troubled muscle function, or Waardenburg syndrome, a genetic cause of deafness. We don't have effective strategies to prevent diseases in category 3. Again, this makes us wonder whether we want to know the disease may be severe or mild or somewhere in between. Knowing early might help life planning or treat symptoms earlier, or just cause more anxiety. Category 4 would reveal early onset brain diseases. So illnesses like Alzheimer's and Parkinson's have very rare genetic forms that strike people in their 30s, 40s, and 50s. So for example, this is about 5% of Alzheimer's cases. Again, we don't currently have a preventive treatment for these early onset brain diseases, but this info could be helpful to make preparations. Results in category 5 assess whether you are a carrier of a gene that might cause disease in your children and your relatives' children, but does not cause problems for you. So, for example, cystic fibrosis, Fragile X syndrome, sickle cell anemia. There are exceptions, but typically how this works is if a person who carries these genes gets together with another person who also carries the same gene, their kids have a higher risk for developing these types of illnesses, many of which don't have cures. So this category is about whether you want to know risk for future children, not necessarily about your own health. So hopefully now you can see this is actually a complex decision, but if you do sign up for genomic sequencing, it's likely you will get to pick which categories of incidental findings you want to look into.
So, what would you choose to learn from your genome? Do you have a question? Or are you ready want to tell me?
Question. For all these categories, right? Is the person allowed to pick like mild and severe, like different levels in each category?
Well, so I obviously stopped the video prematurely because it goes on for another 5 minutes, which I'd like to tell you about other things, but what you then learn that the point is to choose the whole category. You wouldn't have an option to pick and choose certain diseases or levels of risk per category. But the way it's organized is somewhat helpful because the levels of risk are inherently categorized, and so are the diseases in some ways. But you can imagine how challenging it is to even think about these categories and make sense of them and make sure that they're meaningful for people when they are placed in a position to make these choices, which was part of a lot of the research that went in behind the scenes to even come up with these categories that has been somewhat endorsed by member experts in the field. So now that you understand how we've cut up all the incidental findings in these 5 categories, if you had the option, what would you choose to learn from your genome? Hands up for category 1, medically actionable. Oh, ambivalence, interesting. So a lot, but certainly not everyone. Category 2, common disease risks. Huh. So I think roughly the same. Category 3, rare genetic diseases. Oh, okay. Definitely the same hands are coming up. Category 4, early onset brain conditions. Okay, definitely same hands. Mark taking this down. Category 5, carrier status. Okay, interesting. So what's interesting to see is actually your responses mirror very much to some extent with what we've asked patients when we've actually tested with a handful of cancer patients when we were trying to test the usability of this decision aid, make sure that they understand it, they can navigate it, that all the questions and the wording made sense. And when we just tallied some responses as to what categories that they wanted, all patients chose to receive incidental findings, which is very much consistent with literature. But what's not consistent here is that actually you guys did not all mostly choose category 1, which is what they did. And the rest of the categories probably had a little bit more ambivalence than you guys did. But you can see the kind of values and considerations that are taken into account that are going to be different for everybody. Do you have a question?
Yeah, I was just wondering, is there research like this, which is, I have no idea, but let's assume not currently facing large diagnoses versus people who are facing cancer, which is traumatic in the decision-making process, and there can be quite effective because you're looking at a whole bunch of strategies and overwhelming information.
Yeah,
And that can influence decision-making both ways.
absolutely. So in fact, that's the study that we're running soon. We're just developing that survey. So we're going to be taking this into a national survey across Canada to see how members of the public actually their choices in decision making and what they would do based on the results and how they differ based on different groups of patients, just so that we have a pulse. But why would you think that's interesting to make that comparison?
Because I went through cancer treatment, and I remember, and I went through fairly severe cancer treatment, and I remember how overwhelming it is. And if someone had at that point in the first couple of weeks or months asked me to make a bunch of decisions, I'm not sure I'd make the same decisions I would make now.
And that is very much contextualized by that experience,
Yeah, no, absolutely.
always, versus someone who might have not had that experience. So what would you think would be different?
I'm not. I think at the time, I'd either want to know everything because I just would have felt like I needed a lot of information, or I would have wanted to know, at different points, I would want to know nothing because I was just way too overwhelmed, and that causes a entail of anxiety. and
Absolutely.
Stuff like that. Whereas now it's a bit more of an academic question.
Yeah.
I see the age range there, 11. Is that the age range?
So 11 people were over 50 out of the 15. Yeah, so I mean, this is a small sample. It was completely just for usability testing because with every single person, we spent almost 2 hours at the computer going through it and actually iteratively testing and modifying the decision aid, and that's very much classic to that approach. We are running the same study, same decision aid, and actually in a randomized control trial now against genetic counselors to actually validate or see how effective the decision aid is, and it will be over, I think, 150 patients. So we're going to have a bit of it won't, to the extent it'll be representative, I don't know, but at least it'll be controlled.
Age has an impact as well.
And the education level.
Yes, education
Yeah.
level.
Yeah, absolutely. Yeah, yeah. Yeah, lots of those things. Well, in fact, when we asked them in the interviews, so again, part of the work that we do is not only surveys, but we do interviews, in-depth interviews, and not only develop these kind of patient decision aids, but actually sit down for another hour with patients to say, so what's driving your motivation to learn all this information? Why have you chosen the categories that you have? And so what really came out of those interviews when we analyzed them is this very deep-seated enthusiasm for incidental findings, partly because of this perceived importance of the information as empowering. So an example, so here's a quote from one particular patient that said, I think information is empowering. That's why the more information I have, the more knowledge I have to share with my family, the more helpful it is. Other people focused on the information as being helpful to prevent a disease. So one person said around that theme, they said, so I can't change my genetic makeup, but I can change the risk factor by doing more exercise, eating better, and those types of things. For the same reason that you've just identified, people also thought about past health experiences, and that certainly either motivated them for or away from learning more incidental findings. And so this is an example of someone who said, my past experience with a particular health condition has made me not want to choose this particular category. And he or she said, I don't know because I already know about this one disease. So I don't know if I want to know about more at this point in time. So very much similar to what you were just pointing out. And then, of course, that other people just want to prepare, be able to plan for the future. Even though these diseases are not preventable, I want to know what I'm in for. If something is in my future, I can plan ahead of time so I could be more comfortable. And of course, they want the information because it has impact on their relatives. I can prepare my children because I have a son. I would like to let him know that everything that's possible so that he can make his life the best that it could be. There was also this underlying theme when we were talking to these patients and having this very in-depth, deliberative discussion around why is this information so presumably important to you, is because there was this underlying assumption that everything's actionable, not just the category 1 medically actionable category that's been determined to be medically actionable by experts and doctors in the field. It's, yes, it could be treatable, but some variant or information that you could be giving to me, I can act on it by just being able to make changes or change my plans, make changes to my plans, or just create different financial, education, retirement strategies. I'll be able to inform my family members, and so in that way, or maybe seek out other experimental treatments or sign up to trials. Those are ways that they had conceptualized that all the information is actionable. So for example, I still want to know what I'm going to have, if I'm going to have diabetes. Obviously, I'm not going to have that extra donut tonight. I still think even if the interventions are not available, there are still things that you can do. And so this participant number 10 that was the motivation and the thinking behind choosing all the bins. But of course, there were concerns about incidental findings. Naturally, they were feeling overwhelmed, potentially overwhelmed by the information, and that it would provoke some anxiety. And lots of people talked about the issue of genetic discrimination. Having a third party like an insurer or an employer use genetic test results against them when making determinations as to whether they're eligible for insurance or for a job or for a promotion. And certainly that's been a very tangible concern in Canada. In fact, over the last 15 years, I've been working in this domain to actually provide evidence for policymakers to help pass some protection for Canadians around this. There's been a lot of debate over the last 15 years. This is Canada, we have a national healthcare system. Is this really a problem? Do we need rules to protect against genetic discrimination? Well, in fact, myself and others have shown evidence across Canada within the Huntington's population, and in my example of my study, as well as international groups have shown discrimination exists in many different places. In Canada, I found that within the asymptomatic population that I sampled that were at risk for Huntington's disease, which is a genetic condition, who were not symptomatic, 40% of those individuals that were surveyed across the country had reported at least one experience of genetic discrimination, and most of those experiences were in getting denied for life insurance. So after several groups started to advocate for these kinds of laws that needed to be placed, and a Canadian Coalition for Genetic Fairness, which was essentially a national advocacy group that started to coalesce around this and started to advocate to policymakers to actually start to create laws in the country to actually protect Canadians from this kind of genetic discrimination. And luckily, as of 2010, several members of Parliament had proposed several bills. Unfortunately, they died and new ones came up, and those died, and that is a whole other popular science lecture in itself about how laws get passed and how these things go. But finally, in 2013, the Canadian Coalition for Genetic Fairness, along with Senator James Cowan, put together Bill S-201. And it was the most comprehensive, and still is the most comprehensive bill that there is to protect Canadians against genetic discrimination. It essentially says that no one entering a contract or entering into a service or an agreement can ever ask for you to take a genetic test or ever use the results of genetic tests when making any decisions or entering into and providing you a service. And luckily, I'm very pleased to say, as of last year, after 15 years, last May, we got that law passed, that bill passed. Unfortunately, it was passed at the dismay of Trudeau, as well as his cabinet members, who are now actually going to try to appeal to the Supreme Court because it might not be constitutional. So let me circle back and ask you this. Would you still choose to learn what you've just chosen to learn from your genome if you know that your genetic test results are not protected? And if you wanted to learn more about our genomics advisor or hear the rest of the video, please go to this link. Just wanted to end by thanking my lab, as well as a whole bunch of people that I work with and people that fund our research. Thank you very much.